And for the previous method, it's quite simple. Any point not within this span, zero weight. Any point within this span, the weight is 1 over total number of points within the span, right? So very easy. Now here is different. This 20% of the points we will do a weighted least square regression. Well, what's weighted least square regression? Well, we learned it before, and this is one application of weighted least square regression. Now, for weighted least square regression, the variance for weighted least square regression, this is let me write it properly. This is epsilon sigma square v. Weighted least square regression means V is not an identity matrix. And it has this form here. So maybe I should just go back to chapter 5 very quickly for a quick review of weighted least square. So for weighted least square, we are assuming that sigma square V, variance of epsilon, is 1 over W1 and so on. And so this is called generalized least square, one of the special cases. So to do it, that's the weight. Weight is W1, W2, and so on. And then you can fit the model, and obtain this fitted value. And then calculate y tilde. So you got to fit a model first, a least square regression model, and then use that least square regression model to calculate the fitted value. So if you move to another x value, then what do? You determine another 20% of the points surrounding this x1, let's say. Do a weighted least square regression. Get all this estimated. It will be different now for x1. If this is x1, then after you fitted the model, you can get this. So you can see it's a pretty laborious process, right? For each point, you need to fit a weighted least square regression. So that's what happened. So now the next question is, how do you determine all these weights? Well, the weight, so let's just say that, so I've explained this sentence. The last procedure uses, this to generate weighted least square response. Now the weight is given by this function here, according to the researcher who invented this method. The weight is 1 minus t cubed to the power of 3. For some reason, the researcher preferred this weight. Now, so what that means is delta x naught is the distance between x naught and the furthest point in the neighborhood of x naught, of all those 20%. So you will look at all the points among the 20%. Delta x naught is the distance between x naught and the furthest point in the neighborhood. Then the weight given to a particular point is how far that point is from here. So if this point is x0, is exactly x0, then this is 0, this is 0, t will be 0, and then you have a weight of 1 to the power 3, which is the maximum weight. So here I have a sketch of the function here. You can see that if I look at a point that is near x0, then I give it maximum weight. If it is far from x0, I give it a smaller weight. So it will drop very sharply because of the cubic function. And that's how the weights are determined. So let me illustrate what I've said with this figure here. So here is cholesterol, here's H. So for a given x0, I need to find this. Yeah? So for the previous method is very simple. You determine a fixed span B, and then use only those points to calculate this, the average of the Y. But here is different. Here, for the loss method, given a point x0 here, you determine a neighborhood that contains 20% of all the points in the data set. If there are not enough points, you just keep increasing the neighborhood until you get you have 20%. And delta x0 is the maximum distance from x0 to here. So that's the maximum distance. So if you have a point x near x0, let's say this point, then it will have a very large weight given to it. If you use a point here that is far from x0, then the weight given to it will be small. So you can determine the weight using the weight function that I show you. So after you have determined all the weights, you can do a weighted least square regression. And then you will have a model. After you have found the model, substitute x0 into the model to find this. So every fitted value here is estimated from a weighted regression model. So if I want to find the fitted value at this point, let's say 25, then I determine a neighborhood of 20% of the points. Use those points to fit a weighted regression model, and then use that regression model to estimate what is the fitted value. So to get this line, you need to fit a weighted least square regression model for every point here. Suppose you want a smooth curve, then you got to choose more points. Let's say you choose 1,000 points, then you will need to fit 1,000 weighted least square regression model. But is this a problem? Not a problem. Today, the PCs, laptops, they are all very powerful. What's 1,000, You can fit it within a few seconds, or at most a minute, It'll come back and give you a line. So that's the locally weighted least square regression line. So that's the idea, that's the theory behind loss model. Well, all these sound very beautiful, but if you don't know how to apply, you don't have a program to do it, it all remain on paper. So in our program, fortunately, we have a function developed by some researcher. This R is very powerful because the functions, they are contributed by researchers all over the world. Yeah. One day, if you think this loss model is not good enough, you can write one, and then you can publish it, let other people use yours. If you don't know how, then you use this. So how do you fit a loss model? So here I read in the cholesterol data, call this age, call this cholesterol, and then to fit it is very simple. There's no need to choose span, right? Because you automatically use certain percentage of the points, which I believe is 20. Then you fit the model. I would prefer a loss model that give me the ability to choose the 20%, or I want to try 15% or something. Maybe there is. I have not checked out this function carefully, but that's what I do. After that, I calculate Y hat and try to plot it to see what I get. So this is what I get. So what do you think? You know, the fit looks fantastic as far as I'm concerned. It passes through the points closely. I have no complaint. Do you? Well, we can compare all three of them at one go, and you will see, you will have an idea what is the difference among them, and what is the similarity. So the one that is smoothest, of course, is the parametric regression model, because it follows an equation that you have determined. See, this non-parametric regression. The fitted value depends on the neighborhood of points. So it keeps varying, you know, according to the points. It keeps adjusting according to the points. In a way, it's a more intelligent way of fitting a line as compared to parametric regression. Parametric regression is like a dumb way, you know, you just fit an equation. Here, you keep on adjusting, yeah, to it. This one is the same. You keep using 20%, except for the end point, you can't have 20%, I guess. Maybe you would have more points here. Maybe it's still 20%. So you trace out this span and trace out the line. And you can see there is some similarity between these two. Both follow the data closely. But this curve appears to be slightly smoother. Yeah. So this one a bit more variability in the line. Well, so it's a matter of choice. Which one do you want to use? So which one do you like? So there's only one parametric model. The other two are non-parametric approach. All right. So what is the relationship between the loss model and the parametric regression model? Well, for weighted least square, for the loss model, Y tilde can actually be written by S times Y. In other words, this fitted value is also a linear combination of the response, just like the non-parametric regression model. The only thing is, this S here is not the H matrix. It's also not the same as the one that we got using the non-parametric approach. So how do we get this S matrix? get this S matrix, you need to fit n weighted least square regression models. Because you need to fit a model to get a particular yi. So if you have n responses, then you need to fit n weighted least square regression model. And every time you fit a model, you get a beta hat, and then you can calculate this. But that is for y1. Then for y2, you fit another model. That's why I say you need n weighted regression model to get it. All right. Now, there is something interesting, some similarity between the parametric approach and the loss model. So, sum of square residue for the loss model can be defined as observed minus the fitted, just like before, no difference. And it can be written as this in matrix notation. Remember, S is determined by fitting n weighted least square regression model. So you multiply this, factor y out, multiply, you get that. And what is the expected value of this? Well, the expected value of this can be worked out, okay? It can be worked out. I say it's approximately equal to the trace, but I think I want to fill in the blank here. So the blank is here. So let's come to this part for us to understand it. Well, so sum of square residue is equal to this. That's what we have derived. But note that there's a result for finding this expectation of y transpose times ay is equal to this. So this is a theorem, yeah, where variance of y is v and expected value of y is mu. So we are going to apply this to find expected value of sum of square residue. Sum of square residue is of this form. Take a look. A is this, and then you have y transpose and y on both sides. So apply this result, you will get this. And now I say that it's approximately equal to the first one. The second one disappears. Actually, it's not equal to 0, the second one. But asymptotically, that means if you let n increases, the second component there will converge to 0. Now, if that is true, so I say because the testing, this procedure is asymptotically unbiased, so this part will converge to 0, so we're left with this. And then the trace will then become this. So how is this possible? How is this part converge to 0? So we need to come to this. So for ordinary least squares estimate, y hat is h times y. Okay? So expected value of y hat is h times expected value of y, which is x beta. Hx is what? Hx is x. So we know expected value of y hat is x beta. So in other words, y hat is an unbiased estimator of x beta. Now what about loss estimate? The theta value is sy. S is obtained using n weighted least square regression models. So let's try to find the expected value. Well, is equal to S times expected value of Y. Well, so there's one fact that you need to remember. This is theoretical. This loss estimate is asymptotically unbiased. Okay, researchers have proved that. The proof is non-trivial. You know, which means for large sample size n, these two matrices will be similar. Yeah, S will somehow converge to S. And so, if you replace S, this matrix S by H, so replace it, so it's approximately, replace all the S by H, and then this part will turn out to be 0. Yeah. As you have proved a number of results in the tutorial, you can show this easily. One of them will cancel out, and then I minus H, you can show that this is 0. So that brings us back to this one. So finally, we have this result here because of the asymptotic property. And then what happened? So now we know that this is approximately equal to that. So we try to find a trace of that matrix there. You can bring the trace in because trace is just the sum of the diagonal elements. So you can work this out easily, and then bring this over, and you will have an estimate of the variance, sigma squared. So this formula, of course, is different from the parametric version, but is a version that you will get if you do loss. If you use the second approach of non-parametric regression, you can get an estimate of sigma squared. Okay, so I think that's the end of chapter. That's the end of chapter 7C. So let's take a look. What have we done? So in today's lecture, I talk about relationship between parametric and non-parametric regression model. We need to realize that both are similar in the sense that the fitted value for both approaches, they are actually linear combinations of the response vector. Okay? And then we look at the second way of doing non-parametric regression model. So to find the fitted value at a point x0, you determine 20% of the points there. Use those points to fit a weighted least square regression. Then you can estimate y tilde at x0. And do it the same for every other x. You will be able to trace that line, of the loss model. And for R, it's very simple. The function to use is LOESS. And I show you a graph that compares the three models. They look very similar. But I think this third one looks the best. It's smoother than this. Not quite as smooth as this. Maybe this is overly smooth. Yeah, because it has to follow a parametric model. And And then we have estimation of sigma square based on the loss model. Okay, so that is chapter 7C. All right, maybe it's a good time to take 5 minutes break now before we continue, instead of going halfway and then stop. Yeah. And next, I'd like to talk about a topic called response surface methodology. Well, after finishing this course, you can take another advanced course on linear regression. After that, you can take another course on generalized linear model. All this at graduate level. And then you can also take another graduate level course in this one called response surface methodology. So today, I am going to introduce this response surface methodology in maybe half an hour. So we are just going to get a taste of it. So for those who are interested, you can go on to do graduate level courses in this later and spend, I don't know, 30, 40 hours on it. So it's a very big topic. Now, what is a response surface? Well, let's start with some definition first before I explain to you what is response surface methodology and why are we interested in it. Now remember, this is chapter 7. We are still talking about polynomial model. So far, we talk about polynomial model in one variable. Now, in this chapter 7D, I'm going to go beyond one variable and look at polynomial models in two variables. This is one variable, this is another one. So this is the quadratic component of x1, quadratic component of x2, and this term, x1 times x2, is called the interaction term. Right? Now, a proper understanding of interaction term is important in regression. And I will explain it as we go along. So, if you look at this model here, this model. So here is a polynomial model in two variables. And let's say we fit it. You fit it just like any regression model. You can determine beta naught, beta 1, beta 2, beta 1, 1, beta 2, 2, and beta 1, 2. Fit it and get a model. After that, you can sketch this model, sketch the model over these two variables, x1 and x2. In this case, my x1 is concentration, x2 is temperature. So, let me explain now. Why do we want to sketch this? Not scratch, sketch. Sketch this model. This model, this surface that I sketched, using R, of course, is called response surface. So later I'll show you how to do response surface using R. Here is Y. The vertical axis is Y. Well, what that means is, so here I'm talking about a chemical process where the yield, let's say the response is a yield that you will get, from the so-called whatever, let's say in a furnace, you need to have certain concentration of your material and the temperature. After a certain time, you get certain response. So you can measure all this. You can determine the concentration and temperature, and then you can measure the response. So at certain value of concentration and temperature, it can be here. So here corresponds to some other temperature and concentration. So one objective is this. Suppose you are setting up this manufacturing process for the first time. You don't know what concentration to use. You don't know what temperature to use. So you do experiment. You conduct experiment at various combination of concentration and temperature. And then at each setting, you measure the response. And then you can sketch it. It's just like, it's not so abstract. At home, I want to make pizza, yeah? And I know how to make the dough. I do pizza all the time, but once I have the dough, the tomato sauce on it, and maybe some ham and cheese, ham and cheese and pineapple. That's my kids' favorite, called Hawaiian. So after you put them all in, then you put in the oven. And what do you need to do? There are two things you need to consider. For those who make pizza, you will know this. You need to know what's the temperature to use. You need to know how long to let it cook inside. And there's also one unknown factor. You can read from YouTube all this, set this temperature, set this length of time, and when you do it, your pizza turns out to be awful. Why? Because you don't have the same oven that is used by this guy. You have a little oven, so you burn yours while they produce a good pizza. So you need to do experiment. You cannot just follow a YouTube lesson blindly. So suppose I don't know how. I've not done pizza before. Of course I have many times now. Say I don't know, so I'm going to apply what I learned in ST3131. I'm going to try different temperature and different length of time. So I just choose, length of time 20 minutes. I set 20 minutes, 25 minutes, or 15 minutes. Let's say it's 4 settings, 15, 20, 25, 30. And then temperature, 160, 180, 200, 220. So I would have a grid of points here, right? And each point represents a combination of temperature and the length of time. And then I do it. Of course, I try with a small pizza, not to have so much wastage. At certain temperature, then after that pizza is up, So you need to have a way to quantify the quality of the pizza. In this case, I call it the response. So it could be a measure of how good that pizza is for this setting of temperature and length of time. So, you know, if it turns out to be perfect, a score of 10. If it's burnt or undercooked, a score near 0. So you can define your response. After that, you do the experiment at each setting. Yeah? So at each setting, and then measure the response, and then run it. Plot a response surface. And this surface, can you see there's a maximum somewhere, right? So that maximum, you trace it down, you will find the optimum temperature and length of time for the best pizza. That's how you do it. You got it? For example, if you are thinking of setting up a bak kut teh shop, you know, next time, to fight with Song Fa, yeah? Song Fa is very popular here. So you try concentration of pepper, white pepper. That's what they use. I've been there a few times. I've never been there until recently. And I'm quite impressed with it. But it's not my favorite. Of course, for a former Malaysian, this is not my favorite. All Malaysians like dark colors, you know, soup, not the white pepper type. I don't even call it bak kut teh, you know, Singapore version. It's called white pepper soup. If you want to fight with Song Fa, try this. Try different pepper concentration and other spices. Find out what combination gives you the best tasting bak kut teh. Yeah? Sorry, I think there are a few foreigners here. Bak kut teh means what? Pork bone soup. Something like that. Alright, so the response surface methodology is to find optimal setting for response. Okay, so that's the objective. And just now, I described a way of determining this set of control variables, right? Temperature, concentration. I say, just draw a grid. Yeah? You know, research, if you know people do research, statisticians, they find that you don't need to do this. You don't need to say, do this. Then at each point, you cook your pizza one time, you know, and then you find out which one is the best. So this is what I have described to you. So you need 16 of them. 1, 2, 3, 4, 5. 1, 2, 3. How many? 25 points. But there's a more efficient way of doing things. Let's say x1 is one of your regressor variable. x2 is your regressor variable. Don't worry about the unit first. Let's say it's measured in terms of 1, 2, and so on. So a good model to use to construct a response surface is called the central composite design, in which you are going to have a point in which you are going to do an experiment at each of the points. Every point here. So for example, -1, -1, that's 1 point. 1 minus 1, 1 minus 1, there's another point. And then you need to have another point here, following this magic number. It gives you certain optimality. See, what do we want to do? We want to plot a surface over this set of points. You need to have some point here, right? Otherwise you can't. And then in the middle, you have 4 points. You do the experiment 4 times. So that we can check for lack of fit that we have learned earlier. So this is called composite design, central composite design. So if you go for graduate study in response surface, you learn how to design. So this is a simple one. So what about chemical process that I'm going to use it for illustration? Well, the temperature is not going to follow -2, -1, 0, 1, and 2, but it's going to follow this set of temperature for this chemical process that we are doing. See, response surface methodology can be used in kitchen, but it's mostly used in chemical processes. They want to determine the setting for the best yield that they can get. So concentration also has its own units. So you can match it. You can match it with this variable here. So temperature with x1, concentration with x2. So when I say x2 is -2, I'm saying that the concentration is 10. You got it? So if temperature is -1, that means I'm setting the temperature as 200 degrees Celsius. So that's what I'm doing. So let's look at the data set to solidify the idea. Let's not worry about these 2 columns. So I have different temperatures here, different concentration. And then this temperature corresponds to x1, this corresponds to x2, and that's the yield that we get after you perform the experiment. And then there are 12 experiments done in order for us to collect enough data to plot this surface called response surface. And here is the run order. Well, you know, it's prudent to do the experiment in a random order. You don't want to say, okay, I'm going to start with this corner and then keep on going around it. You want to do it in a random order to get rid of whatever biasness that is. See, in the oven that you use to make pizza, you don't want to just change the temperature to the next setting. There might be a remaining heat there. It might affect the outcome for the next one. So this randomization is important. But whatever it is, at the end of the experiment, you should have this set of data. Your response versus x1, x2, or in terms of the actual variable, will be concentration and temperature. Now, how do we estimate? So we have a model, and we want to fit this. We have this data collected, and we want to fit a model here so that we can construct this response surface. The model is here. Here's the model. So based on x1, x2, and so on. So in a way, whatever unit you have, you can convert to this. You can convert to this simpler x1, x2 variable. Yeah. So we have the x variable. See, this x1, this x2. So x1 squared can be obtained from here. x2 squared can be obtained from here. x1 and x2 can be obtained by multiplying these two. So you multiply these 2 columns, you get that. So we have our x matrix. We have our y matrix. You can do least square regression as before to get the regression, estimated regression coefficient. Yeah. Now, this model, after you have fitted, it's very simple. You have done it many times by now. It's in units of x1 and x2. It's in the coded variable. Of course, why would I want to work with coded variable? I want to know what's the temperature I should use for my pizza, what's the length of time. So you can convert this model back to temperature and concentration using this equation. See, when I put this together, when I match this against this, I am actually defining my temperature and concentration in terms of the variables, coded variable x1 and x2. You can check easily. These two are true for determining the relationship between the coded and temperature. Same thing for concentration and x2. So after you have fitted the model using the coded, you can put it back, because what matters to us is T and C, not so much x1 and x2. x1 and x2 is just for us to determine what P and C to use, because you need that 1.414 or whatever, that magical number. So you can use substitution. Substitute into this, you should get this. I think last semester, the last time I taught it 1 year ago, some students substituted it and told me it's not the same. So I said, try again. Then the student said, not the same. Then try again. Finally, it's the same. So I don't know. If it's not the same, then another explanation is, I got this from the book, okay? Now another way is you can simply perform multiple linear regression based on T and C. You can do that. You can get a model directly. So, so that's either you do substitution or you just perform multiple linear regression on T and C. And if you do that, you will get your coefficient estimate here. Here's the standard error for the estimate. And for testing whether the regression coefficient is significant or not, significantly different from 0, we use a p-value. We're not going to test intercept. Intercept most likely is different from 0. That's why we don't test it. So you can see that every one is highly significant. It means this model, at least you feel pretty good now, yeah, maybe this is it. So, here is my R program to determine the regression coefficient. Or you can just fit the model. Here I don't know, I like to use first principle to do it. Find my X matrix, find my X prime X matrix, invert the matrix, solve. Remember I asked you this question during midterm? For students who didn't get it right, remember this. That means you never pay attention when I explain. Or you never do your homework. So you shouldn't get that mark. Fit a model, or I can fit a model. And then this is my full model. And then I can compare this model with the constant model, y equal to beta naught, and test whether 2, 3, 4, 5, they are significantly from 0. So this will test overall model, and then coefficient. So you can do that. To get this table, that's what you need to do. So first of all, test the overall model, see whether the overall model is significant or not. I'm sure it is here. Then you test for individual one, right here. Test for individual, it's also significant. And then do the contour plot. So you need this library here to do contour plot Ly. And it turned out to be a very nice plot here. So you can see for temperature, 180 up to 260. Here's concentration, different concentration. And here it gives you the intensity or the magnitude of the response. So here is what we are looking for. If you want to have the best yield, use maybe somewhere in the middle, trace it down here and here. So let me draw it. So I guess I will take the middle, and you will tell me that I should use a temperature of around maybe 220, 225 here, maybe 22, 23. If I use these two settings, I will get this response. So that's the idea of response surface. Now this is a contour plot. It shows in geography, if you learn in secondary school, they like to show you the contour plot of a mountain, right? It's exactly the same. We are tracing the height of the land. Or if you want to see the 3D plot, you can do it. But I think this contour plot is easier for us to determine the optimal setting. Yeah. So here I have the R program for constructing contour and surface plot. I don't know if I want to explain it, but to do contour plot, you need to set up certain points, right, to plot. Yeah, you need to have enough points. You need a grid of points, and then calculate the y value at each point, and then you can then do a contour plot. Or you can do a surface plot using this function here. Okay? So that's how you can get these two plots. So again, R, thanks to some researcher who gave us these two functions, we can now do response surface quite easily. And for this chemical process, because we intentionally have 4 points at the center, so we can test whether this model is good or not. This is a lack of fit of the proposed model here. Pure error is calculated based on the 4 points. So the degree of freedom is 3. So the residue comprises the lack of fit and the pure error combined together. And you can use this pure error to test for lack of fit. In this case, is there any lack of fit? Tell me. 0.83. What does that mean? So, in case you've forgotten, this is chapter 4. That's lack of fit. in chapter 4, we talk about testing lack of fit. So what is our H0? Our H0 is there is no lack of fit. H1, there's a lack of fit. So for a large p-value of 0.8120, which is very large, so we do not reject H0. So there is no evidence of lack of fit. And after that, since there's no lack of fit, customarily we will continue to use this residue to test for all this. Yeah? So that's what happened. Now, I know this is the end, but let me just explain certain things. So for this experiment, we got a very nice contour plot of this form. So what if I perform the experiment and when I do the contour plot, this is what I get. Instead of this. So what do you think if I get this? Suppose you are setting up a chemical process for the first time. You got a contour plot of this. Well, what that means is your setting is maybe here. So what you see is this. So if you see curved lines without an ellipse, that means you have not reached the optimal setting yet. That's what it means. So the next experiment is, this will be higher value, this lower value. So you need to move your experiments here. Change your experiment. Sometimes you need to do it a few times. Now for the next one, you will start to see curves like this. So whenever you hit the optimal setting, you are going to see this. If you hit this, that means you are at the foothill. You have not reached the mountain top yet. So if you choose your setting to be here, then you will see this. So it says you've got to move in this direction. So when you take this course, response surface methodology, it will, they will discuss how you move to the next set of experiment. You're not going to move to this side, right? You move to this side, you see this. So, what about the interaction term? Interaction term means, do they both jointly affect the yield in some way? See, this is something you want to test. This particular term here, interaction. So your model is this one. So is there any interaction? Interaction simply means, will the temperature and concentration somehow jointly, affect the response in some way? If it is, then beta 1, 2 will be significantly different from 0. Otherwise, it will not. Okay, so in the second half of the lecture, I talk about response surface methodology. It's just a very brief introduction. The idea is we want to find the setting for the mountain top. What is x1 and x2 for us to get that best yield? Yeah, for us to get the best pizza, bak kut teh, or whatever you want to do experiment with. And to sketch a response surface, there are many ways, many designs. Here I introduce one of the simplest design called central composite design, where you have enough points to sketch a contour and also the response surface, and also you can check for potential lack of fit. So I illustrate all this with a chemical process, how we find regression, how we use R to get estimates. This is just like before, nothing new. How to construct contour plot, surface plot, and then we analyze the data. And in this case, I think we have a pretty well fitted model. I've not looked at the R square yet, but everything seems to be significant. So I think it's a good start. Okay, so I think that's all I want to say. I think I'm ending the lecture today early, so it's fine. But I don't think I want to start with chapter 8 today. Maybe we'll leave it to this Thursday to start. So maybe you can do the quiz now, and then we can end today's lecture here. Let me turn on this one first. I set it at 15 to turn on. Okay. So, all right. It's on now. So the quiz today is quite simple. If you can't do it right, then I don't know what to say. Okay, once you're done, you may go. I'm going to change the final time of submission 5 minutes from now, okay?